Hello, Chemistry 30, and welcome to your lesson on oxidation numbers. This is a skill that will help us throughout the rest of redox, and actually even going back in the material you've already done, you'll kind of see how useful oxidation numbers is to even figuring things out like half reactions. So here are the objectives for today. Number one, we're going to differentiate between redox reactions and other reactions using half reactions and/or oxidation numbers. That's actually going to be like a later lesson, but we're learning the base to be able to do that. And then write and balance equations for redox reactions in acidic and neutral solutions by assigning oxidation numbers where appropriate to the species undergoing chemical change. So today it's all about actually learning how to assign oxidation numbers. So we're going to get into it here. So first of all, what's the purpose of oxidation numbers? And this is not quite showing everything, but oxidation numbers, we also call these oxidation states, are used to track electrons in a reaction. So it's a way to keep track of where electrons are going to and where they're coming from. So what we do here is we assign a number to atoms or ions of essentially how many electrons they have. It's a way of like electron bookkeeping, which is what the next slide says. It's just I'm saying the electrons are here with the number that I give it, and then they move to here when I give it a different number. So it's a way of keeping track of electrons, and you'll see that it will become more clear as we go on. So each atom is given an oxidation number which is very similar to its ion charge. It's not the same, but it's closely related. So how do we actually show that it's an oxidation number? Well, one thing we do is we actually write the positive or negative as a symbol before the number. So when we wrote something out, like let's say the calcium 2 positive ion, we actually wrote it as Ca2 positive, and that's a charge when we write the number and then the positive or the negative. Now, when I'm assigning an oxidation number, like for example, if I were to assign an oxidation number to calcium 2 positive, the oxidation number actually ends up being positive 2. And yes, that is identical to the charge. Not always the case, but it is here. Okay, so there's a difference in that oxidation numbers are shown by writing the positive or the negative before the actual number. Oxidation numbers are not an accurate representation. They don't actually literally mean anything. It's just a way of us keeping track of electrons. It's electron bookkeeping. So we're assigning it to something using rules, and then it becomes this really useful number that we can use to track the gain and loss of electrons. In other words, to track the reduction in oxidation that's taking place. So let's take a look at water, H2O. In H2O, I have these two electrons, this bonding pair shared between hydrogen and oxygen, and I also have this bonding pair shared between hydrogen and oxygen. The base idea behind oxidation numbers is that the more electronegative atom ends up getting the electrons that were shared in a covalent bond. Or if we have a complete transfer in an ionic bond, then it belongs to what it got transferred to. In other words, it's just giving the electrons to the more electronegative thing. So if I were to take a look at oxygen and hydrogen, these two electrons that are in this covalent bond, it belongs more to oxygen than it does to hydrogen. So we're going to give it to O for the oxidation number. And same for this right here. We're going to give it to O. So what that means is that hydrogen is left with a positive 1 oxidation number for both of the hydrogens. Okay, so both of these are positive 1. Well, oxygen ends up having an oxidation number of negative 2. Okay, so this works much, much better. Or is a good way of us actually saying that the electrons belong to O from here and from here. We're giving it to oxygen, and then that allows us to track where the electrons go if they end up moving right away from oxygen to something else, or maybe hydrogen gains some electrons, then we can track that throughout the reaction. So we're assigning a number based on putting the electrons with the more electronegative thing. So if you were to look at carbon dioxide, and we're going to learn rules around this to make it a lot easier, but if we actually looked at, let's say, the electron dot diagram for CO2, what we would have is we would have this essentially. So I've got a double bond between carbon and oxygen here, and a double bond between carbon and oxygen here. So these 4 electrons, let me switch colors here. Dum-dum-dum, pens, let's go with red. These 4 electrons are going to end up going to oxygen. So I know they're shared. It's a covalent bond, right? A double covalent bond. But oxygen is more electronegative than carbon is, right? Oxygen is something like 3.2 for electronegativity, and carbon is 2.6, I believe. I'll have to look at the periodic table, but I think that's accurate numbers. So because O has higher electronegativity, these electrons are going to spend more time with O. So O brought 2 of these electrons to the party. The other 2 came from carbon, right? 2 shared pairs. So that means that O will have an oxidation number of -2 here. This O will be the same. It's sharing 2 pairs of electrons. It brought 2. The other 2 are carbons, but they spend more time around the O than they do around the carbon. So this also is going to have an oxidation number of -2. Now, because at the end of the day, this is going to come out to an oxidation number of 0 for the whole compound, carbon will end up having a number of +4 then. In other words, it ended up not having the 4 electrons that it gave in these double bonds, right? They got assigned instead to oxygen. So it's almost like we're treating covalent bonds in our mind as being ionic and giving the electrons to the more electronegative atom that ends up hogging the electrons in these polar covalent bonds. But again, this isn't actually what's happening. These numbers aren't really meaning anything. It's just a way for us to track where the electrons are and how things change. All right, here are the rules. This is the most important slide. If I have an element, even if it's something diatomic like Cl2, every atom in the element will have an oxidation number of 0. So any element at all, when it's by itself, it's 0. Hydrogen is almost always +1, except for if it's in a hydride. So that means that hydrogen is acting as an anion. So for example, if I have lithium hydride, so notice it's with a metal here, and hydrogen is acting as an anion, then it's -1. But almost always with what we're going to be doing, it's going to have an oxidation number of +1 if it's in a compound. So for example, CH4 is +1, and there's lithium hydride again is -1. Oxygen is almost always -2 if it's in a compound, but there's 2 exceptions that you need to know. One is peroxides, and then the other one is if it's with actually fluorine. Fluorine's crazy. It's got an electronegativity of 4.0. So it's going to hog electrons from even an electronegative atom like oxygen. So fluorine would end up getting the electrons, leaving oxygen as being +2 if it was with 2 fluorines like in OF2. So OF2 would be +2. In H2O2, hydrogen peroxide, it's -1. Otherwise, it's going to be -2. I want to see if this will make a new slide for me here. No. Oh, I'm doing all sorts of things that I don't want to do by accident. I'm messing up stuff. All right, let me try to make a new slide to show something to you. Let's say that I'm dealing with H2O. I just want to explain why peroxides have an O with a -1 oxidation number. If I draw the electron dot diagram for hydrogen peroxide, what you'll see here is that I have this covalent bond where it's between 2 oxygen atoms, so equal electronegativity. That means neither one of them actually end up getting this pair of electrons. It's shared equally. But this pair between hydrogen and oxygen, it gets attributed to O, giving it -1, and then this pair gets attributed to O, giving it -1. These hydrogens, of course, will be +1, but that's why in a peroxide, it ends up being -1, is because of the fact that an OO bond is not polar. Both have equal electronegativity. So in other words, it's not going to end up pulling the electrons away in order to get it for the oxidation number. Okay, so O almost all the time -2. Hydrogen almost all the time +1. Atoms and elements is 0. When I have ions, I have the same oxidation number as the ion charge when it's a 1 atom ion. So for example, when I have magnesium, let's say magnesium chloride, it's going to have a +2 oxidation number because its charge is 2 positive. Okay, if I have phosphide 3 negative, it's going to have an oxidation number of +3 because it has a charge of -3. Sorry, I said positive there. Negative for both of those. One thing that you can do, and this is on this slide here, is whenever you actually have an ionic compound, split it up into the two ions, right? And then tackle each ion separately. So often we're looking at polyatomic ions, trying to figure out what the charge is in different atoms in the polyatomic ion. So if we split it apart into our two ions from an ionic compound, and then tackle each section separately, each ion separately, it makes it a lot easier. Now, I know right now you're like, what does this look like? Well, you're going to see in the example. So right now we're kind of getting through the talk, and then we're going to take a look at the examples and actually deal with it, and everything will start to come together. Compounds always have to work out to a charge of 0 because that's the charge on the compound. So the oxidation number will work out to 0 in total for all of that. For polyatomic ions, the sum of all must equal the charge of the ion. So like for sulfate, SO4 2 negative, then if I take a look at all the oxidation numbers in there, it has to come out to a grand total of 2 negative at the end of the day. And then like I just mentioned, for ionic compounds, split it up into its two ions with charge, and then tackle each ion separately, and that will really help. If the rules that you learned in the previous slide don't allow you to solve for everything, just give the most electronegative ion or atom its charge, and then from there you can work the rest out, but that doesn't very often happen. Then from there, this ends up being a little bit of an algebra problem where you're trying to solve what the unknown atom oxidation numbers are based on what you know the total is and what you know for hydrogen and oxygen. Okay, this is from, oh, daughter's here. Hi. And I'm back. So this joke used to be funny when Chuck Norris was a thing, and all jokes were about Chuck Norris. It's kind of over now, but this slide remains. So fluorine, it's crazy. It has such a high oxidation number. It can take electrons even from oxygen. So again, it kind of comes back to the idea that this is really all about electronegativity. Okay, so now let's take a look at some examples. First, oxidation numbers can be fractions, which will bring us to one example, me showing you kind of how that works. And in fact, I'm going to come back to this slide. I think it's important to do that maybe closer to the end to show you how that works while things are, less confusing. So here's how I would do this. Here's an example. I have CO2, and we actually already did this with the diagram, but we can do it again. What I like to do is I like to put the oxidation numbers for each atom, each element at the top, and then I like to put the grand total at the bottom and kind of do my algebra there. So for example, I know that oxygen normally is -2. This isn't a peroxide, right? So it's going to be -2, which means that -2 times 2, I have -4 for a total for oxygen. Now, at the end of the day, I need this to equal 0 because it's CO2, which doesn't have a charge. So I need to figure out what does carbon have to be in order to get to 0? Well, of course, it would be +4 in total. And I only have one carbon, so each carbon atom, well, there's only one, is going to have an oxidation number of +4. So I have +4 and then two -2's, which gives me my overall charge of 0. So what this is saying is that each oxygen has 2 electrons that it didn't come with that we're attributing to it, while carbon is missing essentially 4 electrons from what it started as an atom. All right, so that's the oxidation numbers, +4, -2. Now let's take a look at this one. Oxygen again in NO3- would be -2. It's not a peroxide, so I'm going to give it -2 for an oxidation number. Now this ends up being -6 in total because -2, oh, thanks. Thanks, computer. -2 times 3 is -6. And then I need to get a total of -1. So in order for that to work, I would need nitrogen to be +5. So +5 minus 6 is -1, which means that because I only have one nitrogen, it would be +5 as an oxidation number. H2PO4 minus, I would end up with -2 for oxygen. Based on my rules, I have +1 for hydrogen. So +1 times 2 is +2. -2 times 4 is -8. This whole thing needs to equal -1 because I have a charge here of -1 for the ion. So that means that for phosphorus, it's going to have to equal +5. So positive 2 plus 5 is 7, minus 8 is negative 1. So this P will have an oxidation number of positive 5. One thing that the diploma loves to do is to give you kind of like an element in a few different chemical species and ask you what the oxidation number is in all those different chemicals to show you how much it can change depending on what it's actually with. So for example, if I were to deal with manganese, I could have MnO4 minus aqueous. I could have Mn solid, and then something like MnO2 solid. And it could ask, hey, what's the oxidation number in all of these manganese atoms? Let's add one more. Let's go Mn2 positive aqueous. Just the straight up ion. Okay, so if I were to tackle what the oxidation numbers are for this, let's go with, sure, yellow. For oxygen, it would be -2, right? Because O is normally -2, times 4 means that I have -8. So that would mean that manganese would have to be +7 to come out to the -1 that I have as a total for this ion. So the oxidation number for manganese would be +7 in this case. Here, it's just an element, so it's 0. 0. People often get that one wrong, right? But whenever I have an element, it's just going to be 0 at the end of the day. For this, I have -2 for oxygen, so -2 times 2 is -4. Manganese then would be +4 to equal out 0, the charge for this compound. So I have +4 for manganese. And then finally here for an ion, I have Mn2 positive, so it's just going to be +2, right? It's going to be the oxidation number is the same as the charge because it's just an ion. Okay, some more examples. For number 4, SF6, I know that fluorine, because it's so electronegative, is going to get its charge. So I put fluorine at -1. So times 6 means I have -6 from the fluorines. That means sulfur has to be +6. So that's going to be +6. I have just 1, so it's got to be +6 for the 1 sulfur. All right, H2SO4, oxygen is -2, hydrogen is +1 based on my rule, so -2 times 4 is -8 from oxygens, +1 times 2 is +2 from hydrogens. So now, because it comes out to a total charge of 0, I need to figure out what sulfur is going to be. Well, if I have +2, -8, that has to be +6 for that to work. So +8 minus 8 is 0, so sulfur will end up being an oxidation number of +6. Calcium carbonate, easiest way to actually do this is honestly to separate this into the 2 ions and make it up. So remember that calcium is 2 positive as an ion, and then carbonate is a charge of 2 negative. So really what I'm saying is, hey, for Ca2 positive, what's the oxidation number? And then for CO3 2 minus, what's the oxidation number? So for any ionic compound at all, you can split it up into the 2 ions before you do oxidation numbers, and that makes it a lot easier. So calcium ends up being +2, same as the charge. And then for carbonate ion, I have -2 times 3 is -6 from oxygens. So this carbon would have to be +4 in order for me to get the grand total of -2, which equals the charge for carbonate. Okay, so that's how that would work out. I just split it into the 2 ions, and then from there, I can make it work. So now let's back up to this fractional coefficient thing. I can have fractions for oxidation numbers, which happens a lot with carbon, and it's weird, right? But if I have hydrogen being +1, and then I have 8 of them giving me +8, that was an ugly 8. Let's try that again. Okay. So now for carbon, in order for me to make this equal 0, and for it to multiply by 3 in order to get -8, then that means that this would have to be -8/3 for an oxidation number. It's ugly, but that's okay. We can have that happen. So how I figured that out is it needs to equal -8. I have 3 of them, so -8 divided by 3 is -8/3 as a fraction. So in this case, the oxidation number for carbon is -8/3. Again, really common for carbon. So carbon does this often. It often actually also has an oxidation number of, for example, 0. That happens quite a bit. Okay, but whenever we have like an odd number of carbons and an even number of hydrogens, this is something that is pretty common to have happen. Okay, so filling in this last little blank thing here, if an oxidation number increases, so it becomes more positive, the chemical species is being, well, oxidized, right? It's becoming more positive. It's poo. So this is being oxidized. It's going through oxidation. If an oxidation number decreases more negative, the chemical reaction is becoming reduced. Reduction. Okay. So why don't we do this, because I think that you probably need a little bit of practice. I would like to create a new page here, and I'd like you to try out finding the oxidation numbers for chlorine in the following things. So let's start out with chlorine and HCl. Let's find out what chlorine would be in NaClO3. Let's find out what chlorine would be in Cl2 gas. And finally, let's figure out what chlorine would be in ClO2 minus aqueous. So why don't you take a quick minute, try those out, and see if you can find the oxidation numbers for chlorine in all of those cases, and then see if you're right as I go over the answers here. All right, so here we go. For hydrogen, I know that that's going to be +1. So that means that chloride, like the chlorine here, has to be -1. So this is very simply -1 for that oxidation number. For NaClO3, it's best to actually separate this into its two ions. I don't want to do that here. I'll do it up top. So I have Na positive, which is of course going to be a +1 then. And then I have ClO3 minus, right, as my other ion. So in ClO3 minus, I have -2 from oxygen, giving me -6. So that means chlorine has to be +5 to equal -1 in the end. So this is an oxidation number of +5. Again, with how I'm showing my work, it's the top number. That's my final oxidation number for each atom. So +5 is my answer for chlorine here. For Cl2, this is an element. I don't even have to do the work. It's 0. Okay, that's my oxidation number. And then ClO2 minus, I have -2 times 2 is -4. So that means chlorine's going to have to be +3. I only have 1. So it's +3 for the oxidation number of chlorine to get to that -1 overall charge. So +3 is the answer here. Okay, in your worksheet, this is actually just some answers for that worksheet. I think it's helpful for me to go through this and for you to see the work, but for most of you, you're probably just done at this point and want to zone out or not watch the rest of the video. That's great, but if you want to keep on watching, if you want to try the worksheet and come back to some answers being worked through, well, here it is. So for NO2 minus, I have oxygen being -2, giving me -4 times 2. That means nitrogen has to be +3. So I have +3 for this one here, because I'm looking specifically at nitrogen through these examples. NO2, I have -2, so times 2 is -4. That gives nitrogen +4 here. In calcium nitrate, NO3 minus, I'm actually just going to cheat here and consider only the NO3 minus ion, okay, because I separated the calcium and the nitrate. So I have -2 for oxygen, giving me -6. That means nitrogen has to be +5. So for that one, it's +5. And then for NO3 minus, I have -2 times 3 is -6. So this is going to be +6 for that nitrogen. So I have at the end of the day, +3, +4, +5, and +6. For B, I have -2 for oxygen, so this is going to end up being for nitrogen +2. So divided by 2, that's +1. For NH3, the hydrogen is going to be +1 times 3 is +3, meaning nitrogen will end up being -3 in this case in order to make that work. N2 is an element, so it's just going to be 0. And then for NH4 in brackets 3BO3, I'm again going to cheat. I don't care about the rest of this. I just care about ammonium. NH4 positive. So I have positive 1 for hydrogen, giving me positive 4 total. It needs to come out to positive 1, so that means nitrogen is going to have to be negative 3. So for this, the final answer is I have positive 1 in the first one, I have negative 3 in number 2, I have 0 in N2, and then I have negative 3 in the ammonium borate, or whatever that is. All right, carbon in the following elemental carbon, well, it's an element, so C solid, that's pretty easy. It's going to be 0. Carbon monoxide, I have CO gas, so I've got negative 2 from oxygen, which means I'll have positive 2 for the carbon. For the carbide ion, I believe this is C2 minus for the carbide ion, so that means that it's going to be negative 2 as a charge. I have to look that up on the periodic table though, but pretty sure that's the case. And then for the oxalate ion, I have OOCCOO2 minus, so I have, let's simplify this and just actually rewrite this instead as C2O4 2 negative. So C2O4 2 negative. So I have negative 2 for oxygen, giving me negative 8, which means that I have positive 6 from the carbons. So carbon has to be positive 3 as a oxidation number. I have somebody tapping on my shoulder. 1 minute. Well, there's going to be some harsh transitions in this video, but that's all good, kids. So I was wrong about carbide, so not so bad that I got interrupted there. Carbide is actually C2 with a 2 negative charge, which you can find if you take a look at your periodic table in the polyatomic ions. So that means because I have 2 of them, that each carbon must have an oxidation number of negative 1 in the end. So in summary, for all of these, I would have an answer of 0, and then positive 2, negative 1, and finally positive 3. All right, acetic acid. So that's CH3COOH. We're going to treat every one of those atoms the same. Potassium carbonate will be K2CO3 solid. And then carbonic acid is H2CO3 aqueous. So let's tackle each of these. I actually want to rewrite out acetic acid as C2H4O2 because we're going to treat every atom of the same element as being the same. So for hydrogen, I know that's positive 1. Oxygen is negative 2. So I have positive 4 from hydrogens, negative 4 from oxygen, which means that carbon ends up being 0, which is okay. That can happen. In K2CO3, I'm going to actually just write out carbonate. I don't care about the potassium at all. It doesn't matter to me. Okay, I'm going to split it up into the 2 ions and look at the ion I care about, which is the one with carbon in it. So that's a CO3 2 minus. So I have negative 2 on oxygen, giving me negative 6. That means I need positive 4 for carbon, because again, this has to equal negative 2, right? It has to equal the charge. So carbon is positive 4. And then for carbonic acid, I have negative 2 for oxygen, positive 1 for hydrogen. So I'm at negative 6 here, positive 2. So this means that carbon has to be positive 4. So at the end of the day, my answers for this is acetic acid has an oxidation number of 0 for carbon. For potassium carbonate, I have an oxidation number of positive 4 for carbon. And then finally, for carbonic acid, I end up with an oxidation number of positive 4 as well. All right, that's it for oxidation numbers. Tomorrow, we're going to learn a little bit on how to use this. So we're actually going to be doing a few things with oxidation numbers. One thing is we're going to use this to figure out if a reaction is a redox reaction or not. And then the other thing that we're going to do is we're going to actually do some really intense balancing, like balancing chemical reactions using oxidation numbers as a tool. So what we used to do with guess and check, now we can actually do with oxidation numbers. So that will be what we get into over the next couple of days. All right, that's it for today. Enjoy the rest of your day. Saying day a lot. Goodbye.